In this video, we're going to finish up Chapter 1 in looking at Section 3 and 4. So starting with Section 3, this is a section on measurement. And the main idea of this section is that making careful measurements allows scientists to repeat experiments and compare their results. So the three essential questions that we're going to answer here are: why are the results of measurements often reported with an uncertainty? What is the difference between precision and accuracy? And this is key. This is one of the very important parts of this section. And what is a common source of error when making a measurement? Some new vocabulary that we're going to see here is measurement, precision, and accuracy. And as I mentioned before, these two are very important. So what is a measurement? Well, a measurement is a comparison between an unknown quantity and a standard. So we typically have certain standards like a ruler or a thermometer that help us make measurements. Measurements allow us to quantify observations, and like we talked about in the previous video, that allows us to give a number or some hard facts to our observations. And careful measurements enable you to derive the relationship between two quantities. When comparing results, measurements are often reported with uncertainty. Now, what is this uncertainty? Well, uncertainty gives us a range of measurements in which we would expect future measurements to fall within. So for instance, we may have this measurement here at 14.6, but we understand that our measuring techniques may not be perfect, so we would expect that that measurement is anywhere within the 14.4 up to the 14.8. So we know that the measurement fell somewhere within that range. And that's important because then a new measurement, say a future study that is done, a new measurement that is within the margin of uncertainty confirms the old measurement. So if we do this experiment again and we get 14.7 in here, well, that's within our uncertainty, so that confirms that our previous experiment was correct. And so looking at this graph here, we actually have three different students. And so student 1 had this measure and student 2 had this measure, and we see that student 1 and 2 confirm each other because they overlap, because their uncertainties overlap, whereas student 3 down here may be way off. So there could be something that student 3 is doing that is either incorrect or very different from 1 and 2, or maybe student 3 is the correct one and 1 and 2 are making the same mistake. And so you can find that out through multiple trials. Let's talk about the difference between precision and accuracy. So precision is the degrees of exactness of a measurement. So think of exactness when you think of precision. And accuracy describes how well the results of a measurement agree with the accepted value. I think this illustration down here does a great job of really nailing out the difference between precision and accuracy. So let's look at this first target here. Notice we have lots of arrows really close to the bullseye. So it is precise because we are grouped together. After 3 shots, they're all very close to the same point. We're very exact in our measurements. And it's also accurate because it's hitting the bullseye where we want it to hit. And so to see the difference here, look at this target where we once again have a grouping of 3 arrows real close together, but they're nowhere near the bullseye. So we would say that that is precise because we have a high degree of exactness, but it is inaccurate because we are nowhere near the bullseye where we want to be. And finally, this third example, we have an arrow here, here, and here, and we see that, well, we are neither precise nor accurate, so we call that imprecise and inaccurate. When taking measurements, we want to make sure that we have some good techniques. And to assure that our measurements are both precise and accurate, we need to use good instruments. And we also need to make sure that we use these instruments correctly. So when we use a scale, they should be read with one eye straight in front of the measure. So this is a spring scale here, and on the spring scale, you'll see different tick marks for the measurements, and we want to make sure that when we look at it, our eyes are on the level of the measure. Now the reason we do that is if we are at an angle, like as shown in object B here, If we look at an angle, that creates a different view, and we call that a parallax. The issue with that is you get a different and less accurate reading. And so the person in B here is going to get a different reading than the person in A. So hopefully at this point you are able to answer these questions, these three essential questions, and able to define these three vocabulary terms. And remember to picture that target analogy here to understand the difference between precision and accuracy. Moving on into section 4, we're going to look at graphing data, and the main idea here is that graphs make it easier to interpret data, identify trends, and show relationships among a set of variables. And so we will do a lot of graphing, especially in our labs. We're going to take our data, and to be able to analyze it, we're going to have to graph the data. So what I want you to do is I want you to pause the video, write down what you know about graphing, what you'd like to find out. In this section, we are going to answer three essential questions. First, what can be learned from graphs? Second, what are some common relationships in graphs? And third, how do scientists make predictions? We're going to use a term that you've heard a lot in your math class of slope, and then we're going to introduce these other vocabulary terms that you may have had in your math classes or not, but we're going to talk about the difference between independent and dependent variables, what is a line of best fit, what is a linear relationship, quadratic relationship, and inverse relationship. In any experiment, it is important to first identify your variables. And a variable is a key factor that may affect the behavior of an experimental setup. The independent variable is the factor that is changed or manipulated during your experiment. So the independent variable is what you control and what you change during your experiment. Whereas the dependent variable is the factor that depends on the independent variable or what you're observing. So one thing to remember, independent is what you change, and the dependent is what you observe in any experiment. When you collect data, graphs are a great way to communicate the data and what's going on. They show how the dependent variable changes with the independent variable. A line graph shows how the dependent variable changes with the independent variable. And when we have this linear relationship, we will use a line of best fit, and it's drawn as close to all the data points as possible, and this line is a better model to use to help either extrapolate or interpolate, where you either make predictions of what's going to happen in the future or look at what happens in between your data points. These are terms that hopefully you've heard before. In taking a quick look at this table and graph here, if we look at the table on the right, we can see that the mass attached to a spring in grams is listed. We have 0, 5, 10, 15, 20, and so on. And we can observe the length of the spring. So the mass attached is our independent variable, because that's what we're changing, and we are observing the length of the spring. And so looking at this, we can see, just looking at the table, we can see that, okay, as the spring goes up, as the mass attached to the spring goes up, the length also goes up as well. Well, that doesn't show us a great relationship, whereas a graph shows us a very nice linear relationship. And so when putting this data table into a graph, we're able to see right away, yes, there is a linear relationship between the length of the stretched spring compared to the mass that is attached to the spring. When the line of best fit is a line, then we say that this is a linear relationship between the two variables. And in a linear relationship, the dependent variable varies linearly with the independent variable. Or sometimes we can even say it varies directly. Now that's a special case that goes to the origin, and we'll get into that later. But in all linear relationships, we can write this formula, y equals mx plus b. And so some of your algebra should be coming back a little bit, where b represents the y-intercept and m represents the slope of the line. Now we're talking about this blue line here. We're not talking about the points. We're talking about the blue line, and the y equals mx plus b is the equation of that blue line. Now to review, how do we find slope? Well, that is the rise over the run. And so we look at the line and see, well, how much did we rise over how much do we run? And we find b, the y-intercept, by looking at where it crosses the y-axis. So finding m, finding b, we can then write an equation of the line. And remember, why do we want an equation of the line? Well, then that equation can be a model for our data. It can be a model that we can then predict. Well, let's say we put a mass bigger than 35 grams on it. Let's say we put 50 grams on it. We can use the model to predict how long the spring will stretch. Well, let's say our graph has a relationship that isn't linear. It's not a line. Then it means the relationship between the dependent and the independent variable is nonlinear. So there's a host of different relationships that it could be. We're going to look at two other types of relationships. The first one is a quadratic relationship. And so that's where we get this parabolic curve. And so it's curving as it's going through the data points. It's not linear, that we see this curve and it looks like a parabola, or at least a portion of a parabola. And the equation for a quadratic relationship is y equals ax squared plus bx plus c. Once again, hopefully this is dusting off some cobwebs from Algebra 1 and Algebra 2, where a, b, and c, those are just coefficients, and they can be any numbers based upon the curvature and the rate at which this curves up and to the right. We are not going to spend a whole lot of time finding the quadratic relationships. We'll actually let calculators and the iPads do that for us. But just understand, nonlinear, the first one you may want to look to if you have this curved relationship is a quadratic. The last relationship we're going to look at is an inverse relationship. And that's where as one variable increases, we get a decrease. Now, that's not always the case. That's not the only piece that has to happen, because you can have that same relationship with a linear relationship in that it's just a negative linear relationship, and you can do the same thing with quadratic. But if we look at this curve is a little different than a quadratic. We know it's not linear because this isn't a line, and it's not quite like a parabola. And so if we see that, then we can identify that it is an inverse relationship where y is equal to some number divided by x. Once again, I'm going to show you some techniques in class where we can let the iPad do this for us and identify, using a data set, identify what the relationship actually is. But it helps if we have an idea and we can tell the iPad which one to look for. As mentioned before, there are many other mathematical models apart from the three that we discussed in this video. Such models would be sinusoids, which would represent cyclical phenomena or harmonic motion, and exponential decay and growth, which we could see in bacterial growth or radioactive decay. So there are other models that could come about other than the three discussed in this video. And combinations of different mathematical models can be represented by can be used to represent even more complex phenomena. And so we have these models so that we can predict values. And we take these relations, either learned as formulas or developed from the graphs, and we can use these to predict what's going to happen in the future without having to do any measurement. When I say future, that doesn't necessarily mean a future point in time, but either later on in the experiment by changing the independent variable more severely than what we changed it in our experiment. And so physicists use models to accurately predict how systems will behave, what circumstances might lead, in a solar flare, or how changes in a circuit will change the performance of a device, or how electromagnetic fields will affect a medical instrument. So hopefully at this point you are able to answer these three essential questions and you have a good understanding of this vocabulary.